Hey guys, in this video we're going to be going over parallel RLC analysis and specifically the natural response. So let's get straight into it, right? So what is the natural response of an RLC circuit, right? So basically it's when the circuit is left alone, or more technically, how the circuit will respond naturally. Hence the name natural response, right? So basically what that means, another definition, is typically you'll see RLC circuits with some sort of input, maybe not a voltage source. Let me draw. Or current source. Okay. Typically see an RLC circuit, right? What a natural response is basically there is no input. No input, right? So basically all you're left with is just these three in parallel. All right, so now we know that, let's just go straight into an example. Okay, so let's say we have this circuit. Okay, the inductor, and then a resistor. Okay, and we want to find V, right? We want to find V of t, okay? And we're also given V0 plus equals 12, and the initial current through the inductor, positive, is 30 milliamps, okay? So let's start with finding the parameters of this circuit. Oh, sorry, let me write down the values. So we have 0.2 microfarads, 50 millihenries, and then this resistor will be 200 ohms. Okay, so we need to find our alpha and our natural frequency, right? So alpha is equal to 1 over 2RC, as we saw in the parameters video. And so if we put that in our calculator, we get that alpha is equal to 12,500 radians per second. And this, our natural frequency, is equal to 1 over the square root of LC, which equals 10,000 radians per second. All right? So comparing our alpha and our omega naught, we see that this circuit is overdamped. Okay, it's overdamped. So that means our solution will take the form V of t equals a e to the s1t plus b e to the s2t. Okay, and so let's find our s1 and our s2, right? So s1 is equal to negative alpha plus our damped frequency. And S2 is equal to negative alpha minus our damped frequency, right? Nope, I'm completely wrong, I'm so sorry. Never mind. Spin that back. Right? So, now what was our damped frequency again? Well, in our overdamped case, WD is equal to alpha squared minus omega naught squared, right? So if we plug that into our calculator, the square root of 12,500 squared minus 10,000 squared is 7,500. So knowing that, we know that this is negative 5,000, and this is negative 20,000. Okay, so let's rewrite our V of t. We have now that V of t equals a e to the negative 5k times t, and plus b e to the negative 20k times t, right? And so next, we need to start finding our unknowns, our a and our b, all right? So we need to find two equations. So we know that our v of 0 plus equals 12, right? And so we want our v of 0, right? We know that this is equal to 0 z plus because in a capacitor cannot change voltage instantly. Alright? So that means this is equal to 12. So we bring it into our form equation. We have that 12 equals a times e to the negative 5k times 0, because we're inputting 0 as for t, plus b e negative 20k times 0. And that just simplifies to 12 equals a plus b, alright? So that's our first equation. But we have two unknowns, so we need our second equation for each unknown, right? So let me redraw the circuit. Okay. So let's start with our KCL here in the top node, right? So we know that the current through the resistor plus the current through the inductor plus the current through the capacitor should sum to 0 via KCL, or Kirchhoff's current law. Okay, and so let's just start with what we know. We know that V over R is for the resistor. Let's just keep our inductor as I of L. And we know that C dV dt is for the current to the capacitor. Alright? And so we actually have the current through the inductor here. We know that it's I L 0 plus equals 30 milliamps, right? And for similar to the capacitor, we know that inductors cannot change current instantly, as opposed to capacitors, they can't change their voltage instantly, right? So let's plug in for 0, right? Or let me just write this down. We know that IL of 0 equals IL 0 plus, which we know is 30 milliamps. So we know our V of 0, and then our IL of 0 plus C dV 0 dt equals 0. So let's just move everything to the other side and just isolate this dV 0 dt. So we should get -1 C P O R. Right, this is just an initial. IL 0. Alright, so this is our dV dt. And so let's bring in our form equation, which was V of t equals a e to the negative 5k, right? Yeah. 5k plus b e to the negative 20k t. Right? So let's derive it. So we have dv dt equals negative 5k a e to the, I'm just going to write s1 because just to save time, minus 20k b e to the s1 t. And if we plug in 0, our initial dV dt, it simplifies to negative 5k a negative 20k b. Alright, and so we actually know our initial voltage here because of this, right? So if we plug in that, we get, that dV0 dt equals negative 450,000. And so that also equals negative 5,000 times A minus 20,000 times B. All right, and so now we have our second equation. Let's bring down our first equation, which was 12 equals A plus B. Plug the system into our calculator, and then we should get that A equals 26 and B equals negative 14. So bring that back into our form equation. Our final answer should be V of t equals 26 e to the negative 5,000 t minus 14 e to the negative 20,000 times t. And that is our final answer.